Go over some super generic linear system stuff. I know that Zach has gone over some of this in class. I'll be just a little bit more specific. I'm going to go over some derivative formalisms. So basically, like when we talk about derivatives, what are we talking about and how to place what we're talking about in comparison to the things that you've heard before, like with how people define a gradient, stuff like that. And then I'm going to talk about what I'd argue is like one of the most important fundamentals for this, and that's like a Taylor series, which is like deceptively simple. And we all did this in high school calc, but it's like amazingly important. And there actually are like some weird mistakes that people can make when doing these, and we're going to use these all semester long. So I figured it's important to like kind of drill down on that now. So with that being said, I'll go ahead and get started. So the first thing I want to talk about is dynamic systems. So Zach went over this, but we look at two different types of dynamical systems in this class. The first is a continuous time. This is where I have some x time derivative, some function of the state and the control. And I'll just state control. So unlike in RL, we don't do states and actions with like S and A, we do X and U for everything. So if you ever see X, probably means it's a state. If you see a U, it probably means it's a control. So this is a continuous time dynamic system. So what this tells us is this is continuous time, and that makes this an ODE, or an ordinary differential equation. And then alternatively, what we also talk a lot about, since we have computers, is that sometimes it makes more sense to think about things in a discretized context. So this is a discrete time difference equation. And it's a little more general to talk about dynamics with respect to a discretized model, because there are certain dynamics things that you can only represent in this form that are very challenging to write down in this form. So a good example is dealing with contact. If I had a ball that was bouncing, I could write down a model of that using a discretized model where I encode some sort of logic where it bounces, but I'd have a lot of trouble writing this down as like a smooth ODE for when it makes contact. So not super important, but in general, we're going to use both these representations. This one is generally easier when we're dealing things on a computer, which we almost always are. All right, so the next thing to talk about is we like everything to be first order. First order ODEs. And what I mean by that is that if I were to give you something that looked like this, x double dot equals f of x. This is a second order ODE. And this is super common in the case of like dynamics for a robot or something. But we want everything to be a first order ODE. So a quick trick that we all use to put any higher order ODE into a first order ODE is simply just redefine our variable to have like all these stacked derivatives. And what I mean by that is that I'll do this sort of thing. I'll define my new state to be x dot. And then what I'll say is that the time derivative of this, so add another one, equals, actually, I'll write this out even more general. So I'll just say x dot equals x dot, x double dot equals f of x. And you kind of think, like, what is the point of me writing out this extremely simple equivalence right here? But it makes a little bit of sense when I go and write things out this way. This is 0, 1, I'll do I, just to be general, f0. So what I did here is I took a second order ODE, which was x double dot equals f of x. I basically said, okay, this means that x dot is going to be equal to x dot. That's nothing crazy. And x double dot equals f of x. So now if I redefine my state vector to be x and x dot, I can now write this thing down right here as a first order ODE. So say I'll call this z. I'll call this z dot. So I basically transformed my higher order ODE into a first order ODE. So this is super common with like, if you took a controls class undergrad, they'll talk about like state space. Like the first lecture, they'll be like, here's how we convert higher order ODEs into a state space model, which is what we did right here. Okay, so the next thing is it linear? This is super important and really super simple, which is great. Basically, if it's linear, it should be able to fit into this form. I should be able to go x dot equals a, some matrix as a function of time times x plus b as a function of time times u. And it's really this simple. If it can fit in this form, it is linear. The thing that makes these ODEs nonlinear is that if you ever have like, over here, if you have like x1 times x2, that's nonlinear. If I have u1 times x, or u1 times x1, nonlinear. The rule is that I can't have any of the x's and u's being multiplied by themselves or each other, right? As soon as I do that, it's nonlinear. If I can put it into this form where it's x dot equals some time varying matrix A and some time varying matrix B, then I know I have a linear ODE, right? And this is it definitely trips people up because you can have super crazy things inside these matrices that don't involve linear functions where it's still linear. So what I can have is, just for example, I'll show x dot equals, and I'll put, cosine t squared 1 e to the t plus bu. This is still a linear ODE in x and u. Write that out. In x, u. So when people ask, are your dynamics linear? What they mean is that is it linear in the state and control in x and u, right? So because this thing right here, this is this crazy function and there's all sorts of nonlinearities, but the nonlinearities are all in time. They're not in the state or control, which means I can just write everything down in this ax plus bu and be fine. So that's the story for is it linear? So now we'll talk about, I think before we start like really diving into dynamics and ODEs and control and everything, I think it's worth spending some time and talking about like these like autonomous linear systems. And by that, I just mean linear systems that look like this. So LDS, linear dynamical systems. And this is anything I can write down in the following form. X dot equals a of x. And I'll just assume, x is some vector, a is some matrix. This is my linear dynamical system. And when I say autonomous, it just means that I'm not controlling it. X is defined with this differential equation. It's going to run as it runs, and I have no input into it, right? I can set up an initial condition and just let it run, but at this point, it's just autonomous. And I think a cool way to think about these systems is that they're vector fields, which may sound like a little screwy. So I'll show just some examples to clarify. So here is one example. And then I'll make this a little smaller. Fit 2. Here's a second example. And what we're looking at here is that here are two vector fields that are defined by this ODE. So what this ODE is saying is it's saying x dot equals this matrix times x. And so what I can do is I can plot on this thing x1, x2, and I can go to every single point. I can go right here. I can say, all right, x equals negative 1.3 and x2 equals 1.5. And then I go and I plug that into the x right here. So this x and this x, it's going to spit out this x dot. And that x dot is going to give me the direction of this vector. So all this x dot equals ax is telling me is that it gives me a map where I say at every single point in the state space, it'll tell me what direction that derivative is pointing. So if you can imagine it, if I had like, some flow lines here, what that would look like is if I were to start, say I start my system right here, and I just drop it there and I let it go, this thing will run according to the flow field. Does that make sense? And then same is true for over here. It's the same example. Go ahead and title the x1, x2. And here, if I were to drop something right here, it was going to flow this direction. If I drop something right here, it'll flow this direction. So I like this intuition of, these ODEs that we're talking about, they're really describing these vector fields. And if it's an autonomous system, I kind of just put it in the vector field and just let it like flow. And what we're talking about for linear systems, this vector field is super easy to plot. Nonlinear systems, it could be like a little trickier, and the dynamics are like a little trickier. But right now, we're going to start with linear systems. We're going to feel super confident with linear systems, and then we can talk about more complex stuff. So just to kind of give another perspective of what's going on is that this like flow field interpretation is basically the same as me just doing this. So say I have a plot here of x, t, and t. I'm going to start at some initial condition, x0. So I start at some initial condition, and then governed by this x dot equals ax, it's going to flow some certain way, such that at every single point, this thing right here is x dot t1 and t1 right there. So the two interpretations I laid out are the same. I can look at it as a flow field with a bunch of vectors here that are defined by my ODE. I can talk about dropping things in this flow field and like having it flow, or I can just talk about things in terms of the derivative itself and how, here I have this plot of xt as a function of t, and I start with some initial condition, and then the governing dynamics are this x dot function, and this tells me kind of like how to move as I move. Okay. So now we'll talk a little bit about the stability of these systems. So I'll do stability. Also this, so this whole lecture is recorded, but also the PDF that I'm writing on, I'll add a few things to, and then I'll upload this on GitHub and Piazza as well. So if you were like writing stuff down, like, you certainly don't have to. Stability of x dot equals ax. So this is something that Zach talked about in class. This is super simple. X dot equals ax is stable if the real parts of all the eigenvals of A are negative, if that makes sense. And so what we'll see is that if you imagine, when I talk about stability, what I mean is that if I have x of t, this function of t, and say I have some initial condition here, x0, this would be an example of stable behavior. So this is for the eigenvalues less than 0. If the eigenvalue was greater than 0, this thing would be blown up. So real. So when I say stability, I basically mean for linear systems, its tendency to go towards 0. If it's a stable linear system in this flow field, if you looked up here, if it's a stable linear system in this flow field, no matter where I start it, it'll always come and it'll circle towards the origin. If it's an unstable system, no matter where I start it, it'll always spiral out and go out of control. So that's another reason I kind of like the flow field interpretation of these things. So now we're going to talk about how do we solve this, right? So I'm sure all of you guys have seen things like Euler's method and RK4 and all these like explicit numerical integrators. These are super common. So even though this is the worst one, I'll just describe Euler can tell us, x of, should I write this, time t plus 1 equals x time t plus some time step times x dot of t. So this is certainly an approach to integrating this system, but there's like a lot of structure here that we're not exploiting. So this is a linear system. And basically, whenever you hear linear, you should basically assume there's probably an easy way to do this. So things like RK4 and Euler, backward Euler, all this stuff, that works for any ODE. But we should start thinking about things, because this is linear, what can we take advantage of that would make this easier, where we can exploit the fact that things are linear. So it turns out that we can exactly integrate, like up to machine precision, any linear ODE for any amount of time that we want to. And we do so with the following. So I'll do just new section here, integration. And I'll just, not to, bore everybody with like basic calc stuff, but if you remember, I'll do this just for a scalar. If I have this function right here, I have an ODE that's x dot equals ax, where a is just a scalar. This is a separable ODE, which means I can just rewrite this as dx dt equals ax, and I can do some rearranging, and I can get 1 over x dx equals a dt. And now what I'll do is I'll just integrate both sides. Now I get ln x equals a times t plus some constant. Now I take the exponent of both sides. So what I get is ex equals e at and then plus c, which is the same as eat times ec, which is the same as, since c is just a constant, it doesn't matter if it's e to the constant or just the constant itself. This is the same as me just doing eat times c. So this, maybe you've seen it in an ODE class, maybe you haven't, but this is basically me saying that if I'm given x dot equals ax, I can solve this ODE. This is like one of the few ODEs I can actually solve. I can solve this to get this right here, and it has one constant right here. And how do I determine that constant? Is that comes from the initial condition. So what I say is that whatever my initial condition is, x naught equals e to the 0, since t is 0, times c. So that constant just ends up being my initial condition. So x equals e to the at times x0. So just in that, we've shown if I were to have this system right here, I have x dot equals ax, x of t, and then t. I have some initial condition here, x0. This tells me that this solution right here is described by x of t equals e to at times x0. So linear ODEs I can solve, right? It's very, like, you basically can't solve like any nonlinear ODEs. Linear ODEs we can solve. And what this tells us is that I don't have to do any sort of numerical integration like RK4 or Euler's method. I can simply just solve this ODE with a matrix or with an exponential in this case. And then I get this one constant I get from the initial condition. And now with this function, at any point t, I can just call this function and it would tell me what the value of x is at that point. So this may seem super simple and straightforward for a scalar system, which it is. But what we'll see is that this actually is the same for general, like, higher order systems. So now we'll talk about if I have the same thing, except now I have x dot equals, some matrix A times x, where x is a vector. So this is no longer a scalar. Turns out I can do the exact same thing. I can say x of t equals e to the at times x0. And the one difference is that this is the matrix exponential. So if you haven't seen the matrix exponential, just go ahead and look it up on Wikipedia. It's super simple, but basically it's the idea we extend the Taylor series of an exponential to matrices, and it just works. It turns out that this same property where we can solve ODEs with the matrix exponential if they're linear is true even in the case of like linear systems that are higher than one dimension. So this is this like magical result where if I have a linear x dot equals ax, I don't have to bother integrating this thing using any sort of explicit integrator. I can just solve this system directly given the initial condition, and then I can just calculate its value, at any point in time. So why is this useful? Because now what I can do is I can say x of time t plus 1 equals e a dt times x of t. So now what this is giving me is that given my x dot equals ax, I now have this difference equation. So I started with a continuous time ODE, and I converted this continuous time model to a discrete time model using just the matrix exponential. And again, this is only for linear systems. What this tells me is that I now have this matrix here. I'll call this AD, which you'll see Zach use sometimes. This is our state transition matrix, as it's also called. This is me, I give it one state, x time t, and it's going to push it forward exactly 1 dt. It's going to push it forward to xt plus 1. So what we can do is that all these stability properties that we care about, we can look at them in continuous time or discrete time now. Which begs the question, how do we know is it stable? So before, what we said is that we could take the eigenvalues of this x dot equals ax, we take the eigenvalues of a. the real parts of those eigenvalues must be negative. In the case of discrete time systems, this tells me that the norm, I guess I'll call it absolute value of eigenvals AD must be less than 1 this time. So basically the eigenvalues, like the modulus of these things, if I imagine like a complex plane. So this is like a, real imaginary. They must be within this circle of 1, 1. So this is stable. Anything outside the unit circle is unstable. And this is specifically for the eigenvalues. Okay, so we can determine the stability of a discrete time system. In the case of our linear system, we just, we use the matrix exponential to get this AD matrix. And we'd all have to use just look at the eigenvalues of AD. And if the modulus of these things is less than 1, then it's a stable system. So now we'll finally get into some control stuff. So we're not going to talk about autonomous systems. We're going to talk about systems where we have some sort of active control input. So what this will look like is x dot equals ax plus bu. So now it's no longer just pick an initial condition and let it run. Now we have an initial condition, but we have this control input u that can be whatever we want it to be. So now I'm going to kind of bring it back a little bit more to like robotics. So when we think about robots and how we actually control these things, what Zach mentioned in class is that the control signal is almost always what's called a zero order hold. U, T, T1, T2, T3, T4. And what that means is that it's going to maintain the same signal U for the entirety of the time step. The control signal will look something like this. So to give an example, imagine if I'm controlling like a humanoid robot and I'm looking at like the elbow joint or something. At every time step, I'm going to command a new joint torque. And that joint torque is going to change at every time step if my controller is changing. But it can't change like within the time step, right? So there are other methods where you have maybe first order hold, where I describe the initial point and the derivatives for all the control inputs. But that's really less common than this. So the zero order hold, COH, this is the most common thing that we'll see. And so now knowing that our dynamics look like this and that our control system looks like this, we'll look very explicitly at this period. So we're going to talk about the time between T0 right before in the limit as we get to T1, right? So this section in red right here. And if I had to describe the ODE of this system, here's what I'd say. I'd say that x dot equals ax plus bu. And then what would I say for u dot, right? What I said is that we're doing a zero order hold, so u is not changing throughout this duration. So here I can say u dot equals 0. And all I'm talking about is for just the time between T0 right before T1, right before I change that control input. So what I've done here is I've written out seemingly very simple set of ODEs as a x dot equals ax plus bu, u dot equals 0, so u is not changing. And now what I can do is I can use this and say, okay, well, what's stopping me from writing out a linear system like this, where I kind of stack up x and u, derivative equals x u, ax, bu, 0, 0. And it's important to note that these are the zeros to make square. What I mean by that is that I wrote down 2 zeros, but in reality, when I go and form this matrix, these won't just be like a 0 and a 0. It'll be a matrix of zeros such that this whole thing ends up being square. And I'm going to make a video on this in the future where I go over explicitly how to form these things and the sizing. But basically, I'm going to have a set number of columns here, or sorry, yeah, calls here, and then we can determine the size of everything from the number of rows that we need. But anyways, the point that I'm making here is that this super simple ODE of x dot equals ax plus bu and u dot equals 0, I can write down like this right here. And you'd agree that what I've written down right here is the exact same of what I wrote down right here, right? I didn't, there was no assumptions, nothing. And I'm just talking about the time between t0 right before t1. So if I have it written down in this form, isn't this just another autonomous linear system? Isn't it just another x dot equals ax? But this time opposed to x, it's now x and u. And so it turns out that it is, and I can do the exact same thing I did before. So what I can do is that now I can say that x times t plus 1, u times t plus 1 equals matrix exponential a, b, 0, 0, dt times xt ut. This is like, I now have given myself a discrete time model from the continuous time dynamics. So what this looks like is I end up getting, once I do this out, I'll just do a quick copy and paste. So this right here is going to be super important for us. So we started with the continuous time x dot equals ax plus bu. And what I said is that if I consider the controls as a 0 order hold, so the controls are not changing throughout that time step, I can use my a and b, and I can take the matrix exponential of this combined matrix with times the scalar delta t, and it will spit out this new matrix where I can just pull out the components AD, BD. And what I can do here is I now have my discrete time matrices. So what I can now do is I can now say x of t plus 1 equals AD xt plus BD of ut. So now I have a linear discrete time model where I got my AD and my BD matrices from my continuous time A and B matrices. So this is like, I think this is super cool. This is definitely worth like playing around with and like implementing on your own and making sure that like, oh, you know, if I integrate this ODE with RK4, does it match what my like linear matrix exponential solution tells me it should be? And like what you'll find if you've done it right, that yes, it does. And this is super nice because it lets us describe our dynamics in continuous time, which sometimes make a lot of sense. I can always just convert from linear to discrete, just like that, using the matrix exponential, and boom, it's super easy. This is linear discrete time dynamics. Okay, so I think that that's good for that front. There's one more extension to this, which is in the case of an affine system. So if I were to have some term in the dynamics that wasn't a part of x and u, that I can also similarly just like add another term into this and just make it work. So I won't go through this. I'll let you guys go through this, but I will in this PDF. I will put a section from a paper where they go through this. So I won't go over this, but you guys can just go ahead and read this. But basically, it's saying that if I have a system where it is I have like an affine term, so x dot equals ax plus bu plus d, I can just use the same trick that I just laid out. I can use a matrix exponential, but this time with the identity matrix right here. And what this tells me is that this lets me pull out all the discrete time matrices. So this is just like some extra reading if you guys are interested. All right, so the next topic people have a lot of opinions on. So we're going to talk about derivative formalisms. So basically, when we're talking about derivatives, what do we mean? Why did we set it up this way? And how is it useful for us? Derivative formalisms. So I'm going to talk just from like a generic case. If I have some function f, the way you'll see these things kind of written out is that Rn, Rm. So if you haven't seen something like this, this is, you know, just kind of confusing notation, but basically what it means is that if I have some function, y equals f of x, this is just telling me that y is in Rm and x is in Rn. So basically f is a function that maps from vectors of length n to vectors of length m, which is just this right here. And the reason I'm being like super explicit about this is because when we write these derivatives, the order of everything is going to become super important. So imagine I have y1, y2 down to ym equals f of x1, x2 down to xn. So this, when I write down these sizes, this is what I'm talking about. I'm taking in a vector x, I'm spitting out a vector y. The vector x is of length n, the vector y is of length m. So now the first derivative I'll talk about is the Jacobian. So this is a partial derivative. I write this as partial f, partial x. And what this tells me is that I'm going to have one row for every output of the function and one column for every input of the function. So I'll move this down just a little bit. So dy1, dx1, dy1, dx2, dy1, dxn. And then down here, I do the same thing with one difference. Not opposed to y1, everything here is y2. I'm going to continue this pattern until I reach the mth m. So I'll make this super explicit. Number of rows equals number of outputs. Number of columns, number of inputs. So this is the Jacobian. There's really only one interpretation of this. You'll only ever see this written one way. And basically it gives me a way to write down the first partial derivative of all the outputs with respect to all of the inputs. And we're going to use this all semester. This is super useful. So the next thing that is potentially more popular that maybe you all have seen more often is a gradient. So now I'm going to be super explicit about the gradient because this is kind of where like people tend to like disagree on these things. So the gradient is, I'll look at a specific case. So now I'm going to look at a function where it's a scalar y. It's on a new page. Gradient. So I now have a scalar y equals f x1, x2, xn. Now this is like, a loss function in machine learning is a scalar value function. So it takes in a vector and it spits out a scalar. So what this tells me is that if I were to take the Jacobian of this, following the rules I just laid out, I have one row for every output and one column for every input. So if I write down the Jacobian of this, if I do df, dx, what I get is I get dy, dx1, dy, dx2, up to dy, dxn. And this is a row vector, right? Since I have the number of outputs as I do rows, the number of columns as I do inputs, this is always going to be a row vector. If the output is a scalar, the Jacobian is a row vector. And now this is where it gets weird, is that we kind of just like, to make things easier, we just define this term, the gradient. And we write it down like this. This is the gradient of f with respect to x. And all this is just the transpose of this. So we take that row vector and we're just going to make it a column vector just to make our lives easier. And the reason we do this is because if you imagine if I had like a gradient descent algorithm, I want to add some scaled version of the gradient to the decision variable x. And if they're both row vectors, then the dimensions just kind of work out. So this is really critical that you all know the difference between this. The Jacobian of a function with one output is going to be a row vector. The gradient, this is just simply a convenience thing that we have just made up to say, hey, if the function has one output, well, let's not treat it as a row vector. Let's transpose it, make it a column vector, and let's just call this the gradient. And the reason why this is important is because every single like auto-diffing library, they all use the same convention. If I call it Jacobian, it's going to follow all the normal Jacobian rules. But if I call gradient, it's going to like transpose this thing. And so you'll see this in homework 0. You'll see this all throughout the class. This is pretty important. Now, the next thing is the Hessian. Maybe you've also seen. So the Hessian is written down like this. This is basically a collection of all the second derivatives everywhere. So I won't write this all out. I have instead, I'm going to cheat, and I have this written out right here. So what this is that this is, you can think about it as the Jacobian of the gradient. So it's basically me taking a scalar function. So I have one output and many inputs. And I define all of the possible second derivatives of this. So, as you can see, I have f to x1 and then x2, and which is, since this function is smooth, we assume, which is going to be the same as this will be the same as this. So this is symmetric. So when we talk about the Hessian, this is the derivative that we're talking about. So what's very common is that if the function has a scalar output, doing optimization or something, whatever auto-diffing library or derivative library you're using will let you specify, okay, I want the gradient, I want the Hessian. These are like the things that you'll get if you have a scalar valued function. The Jacobian is like kind of undisputed. Like nobody will ever debate you on like Jacobian conventions. But you'll definitely see some interpretations of this. But for this class, for the books that we use, for all the software we write and that we use in this class, like this is going to be the convention. Okay. All right, we're doing well on time. So now I'm going to talk about Taylor series, which maybe all of you have seen before, hopefully. If not, wait 5 minutes and you'll understand it. It really is that simple. But there is still a good amount of confusion around it. So what all the Taylor series is saying is that if I have some function, so say I have some function, say I have like sine or something, what I can do is that I can take some point. So I'll do x, f of x. I'm going to take some point. I'll call this x bar. And about this point, I'm going to take all the derivatives. So the first derivative, the second derivative, the third, up to infinity. And I can write down a Taylor series that captures all these derivatives. It's going to like spit out to me like the exact function up to some order. So in the case of optimization, this is not super useful to us, anything past the second order. So what I'm talking about a lot right now is first order Taylor series. It's actually probably worth first order Taylor series. And what does this look like? So a first order Taylor series is going to take our linearization point. So this x bar, it's going to look at the function right here, and it's going to evaluate the slope of this. It's going to say, okay, this is the slope. And it's now going to try and predict the value of this function everywhere by just taking the current value and that current slope. So it takes this. First order Taylor. And here's how this looks. So I say that f of x is approximately f of x bar, so the current value of the function, plus df dx, so this is just the slope of the line evaluated at x bar, times x minus x bar. So this notation, the way I wrote things out here are super important. Basically, we have x bar. This is the point that we linearize about. X is this new value I'm trying to approximate the function as. And as you can see here, this function is super nonlinear, right? It's not a line. So when we try to approximate it with a line, we don't do that good of a job. So this is why it's important to kind of stay in the general region where the linearization is valid. So if we're linearizing something, we shouldn't be trying to approximate this thing super far out from where we linearized. The linearization is most accurate right around the linearization point, which we can see right here. So another common way to write down the first order Taylor series, and that we'll use a lot in this class, is we like using deltas for a lot of things. So what we'll do is that we'll say that I'm going to define a new coordinate x, and all x is going to be is x bar plus delta x. So this tells me that if I look right here, I have x is anywhere on this line. So if I were to look at like right here, I could say, if this is x, then that means that this is delta x. So now I'm introducing this delta x And this tells me how far I've gone, positive or negative, from my linearization point x bar. So opposed to defining things in this absolute coordinate x, I'm going to define things as delta x, which just tells me how far away I am from our linearization point. So go ahead and erase that. And now I can rewrite the Taylor series just by substituting this stuff in. So now opposed to f of x, I have f of x bar plus delta x is approximately f of x bar, that doesn't change, plus df dx evaluated at x bar, that doesn't change, and then a delta x right here. So these three lines tell you everything we have to know about a first order Taylor series for a function with one input. And one of the reasons that this that debate over the derivative stuff is relevant is because people will oftentimes try to take a function that has one output and multiple inputs, so a scalar valued function with a vector input, and it will try and form this Taylor series, and it will try and use the gradient right here. But you have to translate, in order to make these dimensions work out, you have to transpose the gradient to make it work right here. And so like if you try to do these things off the shelf and you throw the gradient right here, you'll get like a dimension mismatch. And you'll be like, what's going wrong? Like I'm just taking the Taylor series. And in reality, it's because like the gradient is kind of like fudged transposed version of a special case Jacobian. So when I try and plug this thing into a Taylor series where Jacobians just the dimensions all work out, you'll see that you'll get a dimension mismatch. Not super important. If this happens, like you'll fix it super easily. But this is why people like debate over these things. So this is all we need to know about Taylor series for a function of one variable. But we're doing this class oftentimes has more than one variable. So oftentimes we're doing, x, like the state variable has many dimensions, u has many dimensions, we have many controls. And so we'll write out a more general case. And this will just be a preview. Taylor for dynamics. This would be a preview. This is a super important topic that I'll spend a lot more time on in future recitations. So I'll give you guys just a quick preview here since we're already talking about Taylor series. And what I'm saying here is that if I have x dot equals f of xu, I'm going to define two different Jacobians. So say I want to linearize about x bar u bar. So I chose my two inputs, x and u, as x bar u bar, and I want to linearize this function f around x bar u bar. So what this tells me is that I can do, I can write down everything in the same way that I did previously. I can say fxu is approximated by, and before I do this, I'll define two Jacobians. What I'll call A is going to be the partial of f with respect to x evaluated at x bar u bar, and B is going to be partial of f partial of u evaluated at x bar u bar. And then what I can do is I can write out the Taylor series in two different equivalent ways. So let me just make my space a little easier here. So f of xu is approximated by current value x bar u bar plus a times x minus x bar plus b u minus u bar. And just like before, I can define everything in terms of deltas. So I can say x equals x bar plus delta x, u equals u bar plus delta u. And I can write this thing down as f x u approximately x bar u bar plus a delta x plus b delta u. This is kind of important. This is how we take a first order Taylor series. And here's option 1. Here's option 2. Here are two equivalent ways that we can write down a first order Taylor series for, we use a dynamics function, but for any function that has two vector arguments. Okay. So this general overview I just did for Taylors for dynamics, I went over super quick. This is going to be critical going forward. So in future recitations, I'll spend like a lot more time talking about this, why we do this, and what we can do once we've actually done this. So I think that's a pretty good amount of content for today. So what I'll do is, obviously we have 10 minutes that y'all can ask whatever question you want to. I will take this YouTube video and I'll put it and publish it, and I'll put it on Piazza, and I'll let you guys know when it's uploaded. And then I'll put the PDF here. I'll like clean up a little bit because my handwriting is terrible. And hopefully this is going to be a nice supplement to stuff that Zach's gone over. Yeah. So do you guys have any questions? If so, I'm happy to answer for the next 10 minutes.
You briefly mentioned active control input versus an autonomous system. I was just going to wonder if you could elaborate on the difference.
Sure. So it basically just comes down to, I'll make a note here. These are questions. So autonomous versus controlled. So an autonomous system is this, right? I give it a state. It gives me a derivative. It's just an ODE. I'm gonna solve it using whatever ODE solving technique I want to. A controlled system just has a control input U. So that's the only difference. And normally, like, we choose the U. U is like a signal that like the controller spits out. So if you would imagine like you have like a spacecraft spinning in space. If I turn the thrusters off, this thing is just spinning. It's autonomous. And then I turn the thrusters on. I start like firing thrust, and this is my like U. This is autonomous, controlled. So it's not to say that this thing is like controlled, stable, working well. We've said nothing about like how good of a U this is. We're just saying that a U exists in this ODE. Does that make sense?
Yes, thank you.
Do we submit our homework on GitHub? So the homework will be submitted on Gradescope. Once we finalize a deadline for that, I'll go ahead and send that out on Piazza, and I'll update the Gradescope to have the actual assignment for homework 0, and then y'all can hand it in.
Can you provide a physical interpretation of what Jacobian and Hessian represent?
Yeah, totally. So let's talk about, I think that gradient and Hessian is the easiest thing to like kind of describe. So real quick, I got a question in the chat. So homework 0 is already out. I haven't published it on, so that it's public, but I haven't like published it on Piazza, and we don't have a due date yet. So homework 0 is coming. Don't worry about it right now. Later today, I'll put like an announcement where I have all the details. So don't feel like you missed out on some information. So you want to talk about a physical interpretation of like what these derivatives actually mean. This is a super good question. So if I'm looking at let's look at a super simple function, a parabola. So this is f of x, this is x, and hey, f x equals x squared. So when I take the first derivative of this, what I get is, I'll do 1/2 equals x. Second derivative equals 1. So what I'm saying here is that at any point on this function, I check right here and I want to see, okay, what's the first derivative? The first derivative is going to tell me what the tangent line is. Basically, like, what is the slope of this function at this point? And the second derivative is going to tell me what the curvature is. So in the case of a parabola, the curvature is fixed. It's always 1. So these are things that you've probably seen before. So for a scalar function, this is all super easy to interpret. We have 1D function. So our first derivative, our gradient, is just the slope. And our second derivative, or our Hessian, is just our second derivative of the function. So this is super straightforward. Now let's imagine a more complicated cost landscape, I guess. Shouldn't use that term yet. A more complicated function landscape. So say I have I'm horrible at drawing, so this won't look good. But imagine if I have some like wavy surface here. The gradient is going to tell me like a tangent plane. Yeah, I apologize. I'm about to absolutely butcher this drawing, but the gradient is going to tell me some tangent plane that exists that is like pointing downhill on this function, actually pointing uphill on this function. Depends on how you look at it. So it's going to be a tangent to whatever this surface is. And the Hessian is going to be, it's going to describe like the curvature of this. So if you imagine if this is maybe getting a little bit ahead of ourselves, but if I have a cost function that looks like a bowl, and I go and I at a certain point, I check what the gradient is. The gradient will tell me that there's a tangent plane right here. So the gradient tells me like the direction of steepest ascent. And then the Hessian is going to tell me about this curvature in the form of a matrix. And this will be important later on, but we haven't learned it yet. But basically, the eigenvalues of the Hessian are going to determine like what that curvature looks like. If locally, if it's curving up, if it's curving down, if it's kind of mixed. These are all things that are like really easy to look at that I just am not capable enough of drawing them. But this is a super good question. And next time I'll have some more like visualization stuff where we can look at these derivatives and interpret like what they actually mean. Does that answer
thanks.
your question a little bit?
Yeah, definitely. Thanks.
Okay.
Can I ask you something just about this? So when we take the second derivative, does it just tells us about the convexity or of the surface? So like if it's non-convex or convex?
Sure. So it tells us much more than just convex and non-convex. It tells us like from all the eigenvalues of the Hessian, it tells us, so let's see if there's a plot I can bring. Basically, in the case of I have some positive, some negative eigenvalues, it'll be like a saddle point, which is non-convex, but it's a little more descriptive than just convex or non-convex. But what you're getting at is totally right. So if the function is convex, and I take that second derivative, all those eigenvalues will be positive, which is like geometrically saying that the bowl its curvature is kind of shaped up. And if all those eigenvalues are negative, it means that like it's kind of shaped down. Everything's curving down. And if it's a saddle point, we have a little bit of both going on. So yes, to answer your question.
All right, thanks.
You have any like class logistic questions? Any cool research stuff? I'm happy to answer anything for the next few minutes.
When Zach mentions that optimal control and RL are like kind of two sides of the same coin, I wasn't sure if you want to elaborate on that.
Yeah, this is like a pretty charged topic. And I just talked with a friend about this last night for a while. So they are trying to achieve the same thing, I guess is what he's trying to say there, is that in reinforcement learning, the vocab's a little different, but in general, I'm trying to find some policy that maximizes my reward, right? And optimal control, it just uses kind of different vocab. We're saying like, well, I want to find a policy or basically like the next control input that I can use that's going to minimize some cost. So it's the same idea. They're both trying to optimize over the dynamics of a robot or an agent to maximize a reward or minimize a cost. They're both doing that. The way they do that though is totally different. So I think it's fair to say they're like different sides of the same coin. Like with optimal control, what we're doing is that we're forming these like concrete optimization problems that say, what is the U that minimizes all of this? And with RL, there's like a little more discovery involved, I guess. You kind of have to form these tools that you use to inform your policy. So they're definitely, I feel like when people say like, oh, RL, optimal control, like they're the same. I personally would totally disagree with that. I don't think they're the same. They're definitely trying to achieve the same thing. And it's pretty cool seeing is a bunch of systems that work really well with one and really poorly with the other and vice versa. Like there's things that RL can do that would be like insanely difficult to do with optimal control. But there's also things like a quad rotor, for instance, is like a fantastic system to do optimal control on. It works super well. And RL stuff is, it's good at quad rotors, but there's just no way it'll be as good as an optimal control thing. So they both have their use cases, but I wouldn't say they are the same. So we'll have a little bit of, so I just got a DM, will we have any content or assignment on RL? A little bit. So what we'll do is we'll do some iterative learning control, which is like a super cool kind of middle ground between them, where it's basically using approximate dynamics models and rollouts, and it's taking samples, but it's also using some like second order optimization ideas. So it's kind of like a highly sample efficient RL. And a few years ago, they did some super cool stuff with dealing with quad rotors, dealing with crazy wind disturbances. So we'll do a little bit of RL. This is not like a super RL heavy class though at all. The emphasis is certainly more on optimal control. But there is going to be one lecture whereas Zach is going to go through kind of like a hierarchy of like, here's what RL looks like, here's all these methods, and the cool thing is that he'll describe all of them using all of our optimal control like vocabulary, which is convenient for kind of like placing these things with respect to each other.
On that note, so how good is RL when it comes to implementation on real hardware these days?
Yeah, this is a super good question. I think that hardware is very challenging for like all control systems to actually deploy and succeed on. It definitely seems like RL is having more trouble transferring to hardware than optimal based things are. And I think there's a lot of reasons for that. I think a big one is the quality of the simulator. So sometimes you'll train an RL policy on a simulator that is like doesn't really have the most accurate physics. And then you go on and throw it on a quadruped, and it turns out that there's like a little bit of like flex in all the limbs, and the ground isn't quite hard. And there's like a bunch of differences between your simulation and the real world, which for some reason, some of these optimal control policies seem to be better at handling than the RL policies that were trained just on simulation. But that could very well change going forward. So another DM I just got, do we need a strong background in classical controls for the course? Most of the stuff kind of seems like basics of modern control theory. So I think that it is worth noting that you do not need a strong classical controls background. If you're anything like me, you took a classical controls class in undergrad where you went over a bunch of frequency domain design stuff like root locus and Bodhi. We will not be doing any of that. All we're doing is that the first few lectures, Zach's going to talk about these ideas of stability and equilibrium and stuff like that. And so some control stuff, but you certainly don't need a strong background in classical controls. If you are able to just keep up with everything that Zach is laying out, like you should be totally fine. I think that one of the benefits of this class is that there's no prereq, both in like formally a prereq, but also like I think everything you need to know to succeed in this class, Zach is going to teach you, and it's not so fast that you can't learn it as you go. So if you don't have a classical control background, like no worries. All right, sweet. So on that note, I will stop the recording and I will